Hello, we are from Group 7. Before the presentation start, I'm going to introduce my group members who are Nadra, Amira, Atira, Dikaiser, and me, Ong Yu Hang. The presentation topic is related about the twisted beam caused by the lateral torsional buckling. So, for the first part, I'm going to talk about the visual and detailed inspection that can be carried out. Steel structures are unique in their design and construction. It is a material with many distinct degrees of strength, and all members must be connected properly in order to create a building that is durable. Generally, twisted beam failure is one of the failures in the steel structure. This kind of failure happens when a beam exhibits lateral torsional buckling or improper beam flex. Therefore, structural design and analysis checks are required to study this beam failure. The first test that can be carried out is tensile test, which is known as the one of the crucial tests for the steel bars. A tensile test of a steel material is a destructive process that provides information on sample elasticity, tensile strength, and yield strength. A tensile test is typically performed until the steel samples fall flat or break under the heat. The test includes stressing a steel test piece by a tensile force, for the most part to crack to decide the rigidity, usefulity, and occasion. When a material has high strength, it is mean it can withstand a high level of stress without deforming drastically. The second test that can be carried out is bending test. A bending test is a technique of evaluation the stiffness and yield characteristic of specific materials. Bending tests on steel consider materials with fracture resistance, ductility, fracture strength, and flexural strength. Bending test is frequently performed to evaluate how a material will respond to actual loading conditions. The objective of the bending test on reinforcement steel is to verify the steel's ductility and to make sure that there will be no fracture or cracks formed while bending. Hence, this can help to identify whether the radius of steel reinforcement selected is suitable and prevents it from bending and twisting.
Hi, I'm Amira. I will explain about the assessment of damage and mode of failure. The mode of failure for a twisted beam is lateral torsional buckling. Lateral torsional buckling is defined when an applied load causes both lateral displacement and twisting of a member. Typically, this failure occurs when a load is applied to an unequal beam and the two flanges, which are compression and tension, act in opposite ways. Under the action of load, the compression flange attempts to deflect away laterally, while the tension flange works to keep the beam straight. Forces within the flange also cause the beam to twist about its longitudinal axis in addition to deflecting. The torsional resistance of the beam section determines how resistant the beam is to twisting. Torsional stiffness is affected by the thickness of the beam flange. There are three main factors that affect lateral torsional buckling in beams. First is the location of the load applied. A beam is more susceptible to lateral torsional buckling if the load is applied at a point above the section shear center. Second is the shape of the bending moment. A section with a uniform distribution of bending moment along its length has less buckling resistance than a section with a variable distribution of bending moments. The last factor is end of support condition. The buckling resistance increases when the end supports of the beam section are more restrained.
Hello, my name is Nadra and I will talk about the calculation part. Before we started with the moment distribution method, we have to find the critical moment first without column support. So by using the MCR equation, we have found that MCR without column is 133.71 kN/meter. Meanwhile, for the MED is 600 kN/meter. Over here we can see that MCR is smaller than MED, so the design is not applicable. After that, we have to continue with the moment distribution method. For the step 1 of moment distribution method, we have to find the distribution factor first. Over here is the result of the distribution factor by adding one column at joint P. The coefficient of K of member BD or DB, we use 4EI instead of PEI because we assume that the column is supported by the fixed end support.
Step 2, the calculation, fixed end moment. For fixed end moment, we have three members here, member AB, member BC, and member BD. Member BD is the external column that we added to prevent the lateral torsional buckling. And then since there is no external force acting on the member horizontally, so the member BD experience zero fixed end moment for BD and DB. And for member AB, for clockwise, it is a positive moment, and for anti-clockwise, it is a negative moment. So for a uniformly distributed load, the formula is given by WL squared over 12, and then so we substitute the value into the equation, and we will get the moment for the member AB is negative 100 kilonewton because it is anti-clockwise, and then positive 100 kilonewton for member BA since it is clockwise. And for member BC, since all the load and the length are same as the member AB, so they are the same result. Alright. Step 3 of calculation, the moment distribution. So for moment distribution, we have to sketch the table like this first, and then we insert all the joints A, joint B, and joint C, joint D. So for joint B, we have 3 members here, members BA, BC, and BD. So for the calculation, for DF, the distribution factor is the one that we calculated in step 1, and then the fixed end moment, the MF, is the one that we calculated in step 2. So we sub the value into the table here, and then for the balance, we have to use the fixed end moment times with the distribution factor. For example, the joint A, the AB member AB, we use the 100 negative 100% moment times with 1, we will get negative 100 kilonewton meter. But we have to change the sign, so it will be 100 positive kilonewton meter, and so on. And then for CO, the carryover, CO for member AB will be carried to member BA, and then member BA will be carried to member AB, and then divided by 2. For example, if we want to carry the 100 kilonewton meter from member AB to BA, we have to divide it by 2. So the 100 divided by 2, we get 50. So the carryover for member BA is 50. And then for joint A and C, we know that joint A is a pin and joint C is a roller. Both this pin and roller is located at the end of the structure. As we know, when the pin and roller is at the end of the structure, the moment will be 0. So the final moment is 0 for joint A and joint C. Alright, so how can we get the final moment for others? We have to sum up the fixed end moment, the MF, until all the below parts. So for BA, we will get 150 kN meter positive, and then for member BC, we will get negative 150 kN meter. So as we see the final moment here, we can see that all the moment is balanced. So it is okay. Okay, calculation. For step 4, the reaction. For reaction, we have 2 members here, member AB and member BC. Because member BD doesn't have any external load exert on it, so we negate it. So for member AB, we assume that anti-clockwise is positive, so this is the calculation for calculating the moment, and then we will get the support reaction for RA is 90 kN, and then the reaction for RB1 is equals to 150 kN upwards. And then for member BC, also we assume that anti-clockwise is positive, and then this is the equation for calculate the reaction for RC. So RC we get 90 kN upwards, and then for RB2 we get 150 upwards kN. So for calculation step 5, we have to draw the SFD and BMD based on the calculation previously. So for SFD shear force diagram, this is a diagram, and then the BMD is drawn based on the shear force diagram. So by analyze the SFD and BMD, we know that the maximum bending moment for the structure is 150 kN meter.
After we have found the moment from moment distribution method, we have to find the critical moment with one column support to ensure that the design moment is safe to be used. So by using the MCR equation, we have found that the MCR with one column support is 349.4 kN meter, and the moment that we have designed is 150 kN meter. So the MCR is greater than the MED, so the design moment is very applicable for this project.
Assalamualaikum and hi, my name is Nur Atira. Based on this case study, it can be concluded that the beam failure was mainly because of the design itself. We should take site investigation seriously since the beginning, as it will affect to the structure later. An appropriate and safe design should be made considering of the failure that might happen in the future. The design should be steady and capable to withstand the load for long periods of time. So in this case, we have decided to propose a column as a support for the secondary beam. We have calculated the critical moment of the beam before and after proposing a column. Therefore, the results from our design is that we need only a column in the middle of the beam to support the beam from buckling. Last but not least, more site investigation should be considered during the construction, as it might be that the workers had not done a good job during the beam installation and be one of the reasons for the beam failure. In addition, the labor must have a good skill in installing the beam following as what the engineer desired. This issue should not be taken lightly, as it might be serious failure and might endanger the civilians in the future.